Good afternoon, all of you. My name is Namdev. I am from Department of EEE. And we are going to discuss about the three-phase bridge inverters. Okay. Okay. Actually, for the industrial loads that can be containing motors, we are required okay high amount of the power output power. Okay, high amount of output power we can required. So such that for this kind of uses we cannot use for the single phase inverters. So that's why we are going for the three phase inverters. So then three phase inverters are having high power capabilities, that can have high power capability, and also that can be containing frequency changes. Then that's why we are going for the three phase inverters instead of the single phase inverters. And a three phase bridge inverter consisting so many thyristors that can be containing three half wave inverters. Okay, so that can be containing three half wave inverters. So then go for the three phase bridge inverter diagram. Okay, that can containing three single phase half bridge inverters. That means that is containing six switches or six thyristors and six diodes which are connected anti-parallelly. Okay, then that is having okay, then T1, T3, T5 and T2, T6 and T4, and as well as six diodes are there: D1, D3, D5 and as well as same D2, D6 and D4, and these are connected to a three phase load that may be connected either star or delta. Then take a star connected load. Then this is a balanced load. All three resistors are same. Okay. Then this is A phase, B phase and C phase. Okay. From this diagram, we can say that a three phase bridge inverter consisting how many switches are there? That is containing T1, T3, T5 and T2, T6, T4. Total number of switches are there. Then total number of switches are six switches are there. That is containing total six switches and six diodes. And see this. From this diagram, we can say that that is containing See this leg, this portion of the diagram. This is nothing but a single phase half bridge inverter. That's why this portion is one of the single phase half bridge inverter. This is another one, and this one is another one. That's why a three phase bridge inverter containing total three number of single phase half bridge inverters. Single phase half bridge inverters. And how they are connected? They are connected, see that they are connected side by side. Okay, side by side. So that's why three half bridge inverters are connected side by side. And again we can say that there is a total 6 number of thyristors are there, or 6 number of switches are there that are connected. See, for T1 is connected positive terminal of the battery. Yes or no? C is connected to the T1 is connected to the positive of the source. Again T3 connected positive terminal, and T5 also connected to the positive terminal. At the same time, T4 is now connected negative terminal, T6 also negative terminal, and T2 also negative terminal. So that's why we can say that from each leg, or from each leg or okay, we have total two switches. Totally we have two switches that are connected, one for the positive terminal, another one, second one is connected to the negative terminal of the battery. So that's why we can say that upper group of thyristors or switches, thyristors are all giving positive voltages, and at the same time lower group of thyristors are giving negative voltage. Yes or no? That's why we can say that then T1, T3 and T5 are positive group. At the same time T2, T4 and T6 are negative group. Okay, so by giving output voltage positive, that's why these are positive group, these are the negative group. By clearly observing that 1, 3, 5 are the odd numbers, 2, 4, 6 are the even numbers. That's why odd number of thyristors are positive group and even number thyristors are negative group. Okay, next, then the three phase bridge inverter may be operated in two different modes. Okay, that is depending on the what is the output voltage and what is the switching state of the thyristors. That's why there is a two different kind of modes are there. First one, 180 degrees operating mode, and second one is 120 degrees operating mode. How can you divide this one? By on state of the thyristors. Okay, in the 180 degrees operating mode, each thyristor from each leg, okay, each thyristor from each leg that can conduct 180 degrees of time period. In 120 degrees operating mode, same, each thyristor from each leg that can conduct 120 degrees of the time period. Okay, then go for the first one, that is 180 degrees of operating mode. What is 180 degree operating mode? In this mode, each thyristor or each switch, can conduct 180 degrees of time period. Okay, that can conduct 180 degrees of the time period. So then go for the 180 degrees of operating mode. Then first go for the what is sequence of operation. Sequence of operating of okay. See for the three phase inverter we are giving DC for the bridge inverter, or we are getting three phase output for the bridge inverter. For the balanced three phase load that is star connected, say, then what is the phase difference of each phase? Each phase having 180 120 degrees of phase difference. Yes or no? Okay, that means for phase A starting 0 and phase 2 is 120 degrees for the phase A, and phase 3 is again 120 degrees, phase shift having either A or C. So that's why then operating sequences, we can say that operating sequences then 180 degrees is can be divided into 6 parts, that is 60 degrees, next 6 is that is 120 degrees, 180 plus 60 240 300, then finally we can get 360. Okay, from this diagram, from the bridge rectifier diagram, we can say that each thyristor conducts for 120 degrees from each leg. That means this T1 can conduct 0 to 180 degrees and T4 can conduct from the 180 to 360 degrees. So that's why for the phase A, we can conclude that for phase A that are connected, T1 is conducts up to 180 degrees. Okay, and the remaining conducts T4. Okay, so T1 is conducts up to 180 degrees, from 180 to 360, T4 is conducts. For the phase B, which are the thyristor connected for phase B? From the diagram, and T3 and T6 are connected for the phase B. Yes or no? So then T3 conducts for the duration is 180 degrees, but that can be starts from 120 degrees. Why that is starting 120 degrees? Why? Because each phase having 120 degrees of the phase shift. That's why phase B starts from 120 and that can be conducts up to 300. Why? Because the conduction is 180 degrees. So that's why this is T3. And remaining 120 degrees, remaining 180 degrees, that can conduct negative thyristor, that is T6. So that is 060 and remaining will be conducted here. This is T60. Okay, and next one for phase C. What are the thyristor connected? Remaining thyristors, and 5 and 2 are connected for the phase C. That's why positive thyristor T5 can be starts from where that can be starts? That can be starts from 240. Why? Because that can have again 120 degrees phase shifts. That's why That T5 starts here, 60, 60, 120, and the remaining 60 here. So this is T5. Okay, and from 60 to 240, that can be T2. Okay, these are the phase sequences which are thyristors are conducting. So then each thyristor conducts for 180 degrees for phase A. Then T1 is conducts from 0 to 180 degrees, and T4 conducts for 180 to 360 degrees. And at the same time, T3 starts from 120 and that's end at 360, and again from 360 to 120, that is T6. Remaining T2 and T5 are conducting. Okay, for this phase sequences, we have to go for the phase voltages. What are the phase voltages? Then go for one by one. From 0 to 60 degrees. Say that we have total 6 dividers are there. 6 time intervals are there. Okay, for each time interval, that means from 0 to 60 degrees, what are they conducting? From phase A, T1 is conducting, phase B, T6 is conducting, and phase C, T5 is conducting. And at the same time, from phase A, 60 to 120, that is T1, and phase 2, that is T6, and phase 3, T2 now. Again from 120 to 180, from phase A, that is T1, phase B, that is conducting. Which one is conducting actually? This is starting T3. So T3 and T2. Okay, again same from 180 to 240, phase A, that is conducting T4, phase B T3, and phase C T2. 240 to 300, T4, T3, and T5. Again T4, T6, T5. These are the sequence of thyristors which are conducting. So then go for the 0 to 60 degrees. For 0 to 60 degrees, 0 to 60 degrees time interval or time interval 1. Which thyristors are connected for the load? Then observe from the diagram of the bridge inverter. From 0 to 60, then which are connecting? T1 is conducting, yes or no? Then T1 is conducting. Again redraw the diagram. Which one? T1, T3, T5, T2, T6, and T4. Okay, and load is star connected load. Okay, now okay, for the first interval 0 to 60 degrees, which are conducting? They are conducting T1, T6, and T5. So from upper group T1 is there conducting. Okay, and second one T6. Okay, then T6, and next one T5. So T5, that means from 0 to 60 degrees, then what is circuit they appearing for the load? That is from upper group. Okay, 0, T1 to A, Okay, this is A, and next one from T6, that is connected minus, so T6, and from T5, okay, from T5 that is connected to the C. Okay, so this is C, and remaining is B. So these are connected to the directly like this load. This is Vs. Vs. Then load is balanced. That's why all impedances are equal. For analysis, easier analysis, we can assume that the resistive load only. Then what is total current I? Okay, say for interval I1, first interval I1. Then first find out the what is R equivalent. R1 and R both are in parallel, so that's why R into R by R plus R, and remaining resistor is in series. Then we can get R square by 2R plus R by 2 R by 2 plus R. Then we can get R plus 2R divided by 2. So that's why the total resistance is 3R divided by 2. This is R equivalent. Then what is current? What is total current? I. We can get I or I1, that is equals to VDC divided by R equivalent. Then VDC or Vs divided by what is R equivalent? That is 3 by 2 R. Okay, from this we can get total current, that is 3 VDC VDC by 3R. Okay, this is the total current flowing in the circuit. This current, that is 2 VDC by 3R. And clearly say that for these two, for phase A and phase C, both resistances are equal. That means both impedances are equal. Then the current can be equally divided in between these two phases. That's why this total current can be divided equally. Yes or no? So then we can find out what are the voltage across the each phase. Voltage across each phase, that is VA or VAN. Okay, so this terminal is neutral. VAN, that is nothing but current into resistance R. Okay, that is again equals to VCN. Why? Because both are in parallel. Okay, VAN is equals to the VCN. So that's why, what is I actually? What we are getting I? I is nothing but 2 VDC divided by 3R into R. Okay, then we can cancel out each other. That's why we can get 2 VDC by 3R. 3. Okay, so 2 VDC by 3. That is nothing but voltage across the VAN and VCN. Okay, then what is voltage across VBN? Then VBN is nothing but total current flowing from the this phase R resistance R. So that's why VBN, that is equals to I into R, that is I1 into R, that is 2. 1 minute. We have 2 also here. Okay, 2. So then 2 VDC by 3R into R. So then RR is cancelled out. Now finally we can get 2 by 3 VDC. VDC. So finally we can conclude that. We are getting phase voltages from 0 to 60 degrees, that is VAN is equals to VCN, that are 1 by 3 VDC, this voltage 1 by 3 VDC or VS. Then what about VBN? VBN is nothing but 2 by 3 VDC. But from diagram we can see the negative terminal is connected to the B phase. Yes or no? Negative terminal is connected to the B phase, this one. Okay, so this one is, so that's why this voltage is negative value. So finally we are getting VAN and VCN are both are equal, that is 1 by 3 VDS, and VBN is nothing but 2 by 3 VDC. Then draw the waveforms for this VAN, okay, and VBN and VCN. What is values of VAN? That is 1 by 3 VDS, positive. Okay, so say this is 1 by 3 VDC from 0 to 60 degrees. What about VBN? We are getting VBN, that is minus 2 by 3 VDC. Okay, so minus 2 by 3 VDC. So that is like this. Okay, its magnitude is double about VAN, and VCN is also 1 by 3 VDS, that is for 0 to 60 degrees. This is from 0 to 60 degrees. And same we have to calculate. Same we have to calculate 60 to 120 degrees. From 60 to 120 degrees, we have to calculate same values. VAN, VBN, VCN. Then what are the thyristors are conducting for 60 to 120 degrees? Which thyristors are conducting? Then what is the sequence of thyristor conducting? From okay, from 60 to 120 degrees, T1, T6, T2 are conducting. Okay, so 60 to 120 degrees, they are conducting T1 is conducting T2 and T6. Okay, so T1 and T2 and T6, these are the conducting thyristors. Okay, so again redraw the circuit. From this diagram we can get from T1 is conducting, that's why that is of upper thyristor, so positive voltage getting at V1. So then phase A, and T6 is conducting, that is negative, so T6 is conducting, so T6 is connected to the B phase, and T2 again connected to the C phase, and this is also negative terminal of the battery, so that's why we can get this circuit. Then all impedances are equal, RRR. Now again you can find out currents. Okay, so that's why in this operation also we can get resistance R equivalent, same value, that is 3 by 2 into R equivalent. Then what is I2 now? I2, that is also VDC by R equivalent, so that is VDC divided by R equivalent, that is 3 by 2 into R, 3 by 2 R. Okay, so from this we can get 2 VDC by 3R. This is the total current I2 for the instant of 60 to 120 degrees. From this again we can calculate the voltages of the each phase. Okay, then what about this one? This is VAN. VAN, then VAN is nothing but, see, the total current is flows from the VAN, that's why the voltage is nothing but I into R. So that is I2 into R, that is I2 is 2 VDC by 3R into R, then R cancel out. Okay, then what about remaining two resistors? This is the B phase and this is C phase. Okay, B phase, C phase are connected parallelly, that's why they can get same value. Then VBN and VCN are same voltage we are getting, that is, and current also equally distributed in between those two phases. Okay, so current also equally distributed, equally divided, that's why the voltage I2 by 2 into R, then that is 2 what is I2, that is 2 VDC by 3R divided by 2, that is 2 into R. So 2 cancel, R cancel out, we can get VDC by 3. Okay, then conclude that finally from this we can conclude that what are the voltages we are getting, phase voltages from next instantment, that is from 120 to 60 to 120 degrees. VAN that is 2 by 3 VDC, and VBN is equals to VCN, that is VDC by 3, and say that the thyristors T6 and T2 are connected to the negative terminal of the source, that's why this voltage is negative value. So now again you have to draw these voltages in terms of phase voltages. Then from 60 to 120 VAN, that is 2 by 3 VDC. So this is what is this 1 by 3 VDC. Okay, next 2 by 3 VDC must and should be higher than the 1 by 3 VDC, that's why we can get this kind of waveform. Okay, and next one, what about VBN and VCN? VBN we are getting minus VDC by 3. Okay, so VBN already we are in minus, that's why this is minus VDC by 3. And what about VCN? VCN, this is positive VDC by 3 and we are getting minus VDC by 3. Okay, so this is for 0 to 60 to, this is from 0 to 60 degrees. Okay, this is 60 to 120 degrees, this is 120. Okay, it's the same way again you can go for the next instant, that is from 120 to 180, that is 120 to 180. From 120 to 180, which thyristors are conducting? From sequence diagram we can say that from 120 to 180 T1, T3 and T2. Okay, so 120 to 180, 120 to 180 we are conducting T1, T3, T1, T3 and T2 and T2. Then redraw the diagram, redraw the circuit diagram by this instance, which are the conducting. So T1 is conducting, okay, T3, so T3 is conducting, then T2 is conducting. Now redraw the circuit diagram by this instance. T1 and T3 are the upper group, that means positive values are there, then positive terminal is connected, and T2 is negative 1. Okay, so phase A, B and C. Now again you have to calculate remaining all values. What is, we are getting R equivalent in previous case, we are also giving same R equivalent in this case also. for R equivalent we are getting 3 by 2 R, 3 by 2 R. And what about I3? This case we can say the I3, what about I3? I3 is nothing but VDC by R equivalent. We are getting same values always this case. Okay, so then VDC divided by R equivalent is 3 by 2 R, that is nothing but 2 by 3 R. Okay, then again calculate the phase voltages. What about A phase? These phases are connected in parallelly, so again VAN is equals to VBN. So these two are parallel, that's why we can get 1 by 3 VDC directly. We are not going any calculations. In the previous case we are seeing that. Then what about VCN? VCN, that is 2 by 3 VDC. Now again redraw these phase voltages in waveform. Then VAN we are getting 1 by 3 VDC, and VBN we are getting 1 by 3 VDC, and VCN we are getting minus 2 by 3. See, why minus? Then C is connected to the thyristor T2, that is connected to the negative term of the battery, that's why this value is minus. Okay, so then that is like this. Okay, so that is up to 180 degrees, up to 180 degrees. Then we have completed half cycle. We have completed 0 to 180 degrees. For next half cycle we have to calculate all phase voltages, otherwise you can repeat the same cycles. You can repeat same cycles. Then I am repeating same cycles. For next one, negative 1 by 3 VDS for phase A. Okay, so from 180 to 240. Okay, and for next one, that is minus 1 by 3 VDS, that is up to 300. And for next 300 to 360, that is minus 1 by 3 VDS, 360. This cycle can be again repeats from next 60, 120, 180. For next one, that is VBN, that is VDC by 2. Okay, and next minus we can get like this. Okay, for VCN positive like this. Okay, so from each phase we are having 6 steps of voltages are there. From 0 to 60, 1 by 3 VDS. From 60 to 120, 2 by 3 VDC. Okay, again from 120 to 180, that is 1 by 3 VDC. So like this, each phase we have 6 different steps. That's why this inverter is known as 6-step inverter. 6-step inverter. Now go for the line values one by one. We have to calculate the line values, line voltages. Line voltages from 60 to 0 to 60, first one. What about VAB? What is line voltage actually? The line voltage is nothing but voltage across any two phases. That means from this diagram we can say that this one, the voltage across any of the two phases are VAB, VBC or VCA. Okay, so that's why the voltage across any phase, any two phases is nothing but difference of the phase voltages of that particular lines. So that's why VAB is nothing but VAN minus VBN. Okay, so then what is VAN for 0 to 60 degrees? VAN, that is 1 by 3 VDC, 1 by 3 VDC. And what about VBN? VBN minus 1 2 by 3 VDC. Yes or no? So that is minus of minus 2 by 3 VDC. Okay. So then calculating VAB 1 by 3 VDC minus minus plus 2 by 3 VDC. Then finally we can get that is VDC. That is VDC from 0 to 60 degrees. What about 60 to 120 degrees? What about 60 to 120 degrees? 60 to 120. What about VAN? VAN minus VBN. So that is 60 to 120 degrees. VAN 2 by 3 VDC. 2 by 3 VDC. 2 by 3 VDC. And what about VBN? VBN minus 1 by 3 VDC. So that is minus of minus, that is plus 1 by 3 VDC. That's why again we can get VDC. Okay. So from 0 to 60 VAB we can get VDC from 60 degrees. Again VDC for next 60 degrees, that is up to 120. Okay. Then what about next one? 120 to 180. For 120 to 180, what is VAN? VAN, that is 1 by 3 VDC. 1 by 3 VDC minus VBN. VBN also 1 by 3 VDC. So 1 by 3 VDC. So that's why VAB for 120 to 180, that is 0. So we cannot getting any voltage for this period. Okay. So this period we cannot get any voltages, that is 0 up to 180 degrees. So 60, 120, 180. Okay. Next, for the next cycle we can repeat it directly. For next half cycle from 180 to 360 we can repeat it, otherwise you have to calculate, no problem. Okay. So for next cycle that can be repeats. $240 and 300, up to 300 we are getting voltage. For next 60 degrees there is no voltage, 0 voltage. For next 6 degrees we cannot get any voltages, that is 0. So for 360 degrees this is the phase A voltage. And same VBC also, we can find out VBC also in the same way. For VBC 0 to 60, what is the VBC? VBN actually that is minus 1 by 3 minus 1 by 3, sorry, minus 2 by 3 from 0 to 60, that is minus 2 by 3 VDC VBN. So minus 2 by 3 VDC minus what about VCN? VCN is 1 by 3 VDC. So minus of minus is plus 1 by 3 VDC 3. So minus VDC plus VDC. So that's why we can get minus 1 by 3 sorry, this is minus. Okay, minus. So then we can get minus and minus, that is minus VDC 3 VDC. So then we can cancel out one other, that is minus VDC. So from 0 to 60 degrees, that is minus VDC, like this. Okay, next one, for 0 to 60 to 120 degrees, 60 to 120 degrees, whatever VBN, 1 by minus 1 by 3 VDC. So minus 1 by 3 VDC, and VCN, that is also minus 1 by 3 VDC. So minus of minus is plus 1 by 3 VDC. So that's why we can get 0 voltage. From 60 to 120 degrees, we can get 0 voltage. So from 60 to 120, there is no voltage anymore. Okay, next one, from 120 to 180. From 120 to 180, VBN is minus, VBN is 1 by 3 VDS, 1 by 3 VDC, and VCN is minus 2 by 3 VDC. So that is minus of minus plus 2 by 3 VDC. So that's why we can get VDC. Okay, so for the next period, we can get VDC. Okay, and likewise for next period also we can get this one, and next one 0. Okay, minus. So likewise we have to calculate VCCA also. Okay, then find out the RMS voltages VAN or AB, that means line RMS voltages, that is nothing but line RMS voltage. Okay, so line RMS voltage is, then each line voltage conducts up to, that is conducting from say VAB, that is conducting 0 to 120 degrees. Okay, so that is conducting 0 to 120 degrees. And what is time period actually? That is time period is 1 by 80. Okay, so 1 by pi, that is conducting 0 to 120 degrees. Then VAB RMS, that is 1 by pi, that is conducting from 0 to 120 degrees, that is 2 pi by 3. And whenever that is conducting, what is value? That's value is nothing but VDC. So that is VDC and d omega t. Then by integrating, and this is RMS value, we can go under root 1 by pi V DC square under root of integration of omega t. Integration of 1 is omega t, then 0 to 3 pi by 2. Then calculating values, then we can get VDC under root 1 by pi Then apply upper and lower limits, that is 3 pi by 2 minus 0. Okay, so finally we can get line RMS or VAB RMS, that is VDC, then cancel out 1 by 1, pi cancel, then 3 by 2. Okay, then what is phase voltages? Phase RMS value of phase voltage, then that is VL by root 3. Then VL is nothing but RMS voltage of the line value, then that is VDC under root 3 by 2 divided by root 3. Okay, then we can get VDC by root 2 into 3. Okay, so then finally 3 by root 3, sorry, VDC.